We saw in the last video that the magnetic force from a uniform magnetic field on a current carrying loop of uniform current is zero. The total force is zero. That does not mean, though, that nothing goes on, right? That just means the total force is zero. So I've drawn, poorly, but I've drawn basically a current carrying loop that's encased in a magnetic field. I've again made it rectangular. I think the last video it was a square, but we'll say this is a rectangle of side A and side W. And what I've done is I've basically gotten a way for the current to get into this loop. If you're looking at the last one, you go, well, what do you mean a loop of current? You've got to have a voltage source for current to flow. That's going to mess up your loop. And you're probably right, but what I've done here is this is assumedly attached to some voltage source down here. Current's flowing in through this path, and then it takes a trip around the loop and flows out through this path. And I'm going to assume that I've put these wires so close together that, of course, I can't let them exchange information, so they're well insulated. But I put them so close together that basically I'm going to approximate this thing as a closed loop of current. So if this is side A and this is side W, that means this is side A, and that means this total thing is side W. Technically, I've got a little break here. What I'm saying is this is going to be so close together that I'm just going to consider this to be one long current of side W. Okay, what happens? Well, force-wise, nothing. There are no forces exerted on this. But, all right, as far as, I should say, there's not a net force. There are definitely forces exerted on each side. We saw in the last video that they cancel. But let's look at this in a slightly different viewpoint. So, as I've drawn it here, we're going to move up to the top and look down on it, which is what I've drawn here. So this current coming up the leg here is this current here. This current coming down is this current here. And that's going to be the case in every situation. Of course, let's put a little geometry in there. See if you can read this. This length is W, right? This is the side of A and this is the side of W. Of course, you can see the current here. But this is the side W. Now, let's furthermore assume that this conduit for the current is also going to physically serve as an axis of rotation. In other words, this thing is constrained over here, but it's constrained in such a way that this whole thing can rotate. That's going to be important because we're going to find out in just a second that it does actually rotate, but we'll assume that the geometry is nice, and so this dotted line I've drawn of the axis of rotation is going to intersect this side exactly in the middle, which means that's somewhere about here where I've drawn the arrow for the current, which means, of course, that this distance there is W over 2. This distance is W over 2. Okay, so what are we going to do here? Let's look at the forces that are being exerted on the legs that are coming into and out of the page. We'll ignore this for now. We're going to look at the forces here and the forces here. So this one, put my fingers in the direction of the current. That's into the page as I've drawn it. Fingers in the direction of the current goes down. Curl them into the direction of the field. That looks like this. So fingers down to match the current. Curl them into the field and then stick out my thumb. I get a force acting, a different color here. I get a force acting on this side that is down. Now, I know what that force is because I know the geometry and I know B and I. That force, and I'm only going to write this one time, that force is IAB. I think you can see that. How do I know that? Well, I've got the general formula is the magnetic force is ILB sine of theta. In this case, notice theta, the angle between the current and the magnetic field, theta is always going to be 0. This current is always acting perpendicular to B, 0, 90 degrees. The angle between the current and the magnetic field is always 90 degrees. Sine of theta is always going to be 1, so I can drop the sine of theta. The length of this wire is A, current is I, magnitude of the field is B, so I get that the force exerted here is IAB. It's going to be the same over here for all the same reasons. IAB, that's this leg, and the Actually, that's this leg. This current is this one. This current is this one. But same considerations, side A, I, and B. So the magnitude is going to be the same, but over here I've got a different direction. We saw in the last video, if a current into the page produces a downward force, then a current out of the page is certainly going to produce an upward force. Check it with the right-hand rule if you want to. That's fine. So I get that. Now, if you're paying attention, notice what's going to happen. If this thing is free to rotate, it's going to. You've got a force over here pushing up. You've got a force over here pushing down. This is going to rotate the system, which is why I stress that this thing will serve as an armature. It will allow this system to rotate. It forms an axis of rotation. So I'm allowing it to rotate in this direction. Now, I'm not allowing it to rotate like this. Physically, this is going to be constrained, not like this or like this, but only to rotate like this. So that's why I don't need to worry about forces and torques on this side and on the underside, which is kind of back behind the page, is because physically those torques will be counteracted by an external torque produced by the mechanism. In this case, though, I'm allowing the torques that seek to turn it like this to exist because I've constructed it such that that's okay. That's why I'm not worried about any forces or anything acting on this particular leg. I'm just looking at these two. It's physical constraints. Well, as soon as I have that, and as soon as I recognize that in every one of these cases, this force is not going to change direction because the current and the magnetic field haven't changed directions, then I can go ahead and put in that force everywhere. My pen is failing. Alright, so what I've done, now that I put in the forces, is I've drawn this in different orientations. If I turn on the magnetic field or turn on the current, either one, or turn them both on when the apparatus is in this situation, we've seen it will try to rotate. At some point later, it'll look like this. There's still a torque acting on it, so it's going to continue to rotate. At some point later, it'll look like this. We'll talk about this in a second, but if you're clever, if you paid a lot of attention in Physics 1, you might recognize that there is no torque in this situation. We'll talk about why in a second. But it does have inertia, and it will continue to rotate through this position to over here. So look carefully. There's still a torque acting here, but what does that torque want to do? Well, now the torque wants to rotate it the other way. So as the system evolves from here to here to here to here, the torque is changing. If there's a torque here, but no torque here, we'll look at the math in a second. But if there's a torque here and no torque here, then it's changed. And then if it has an oppositely directed torque here, then it's continued to change. So what I want to point out is that, remember, torque involves not only a force, but a perpendicular distance, or a moment arm, if you call it that, which I like to. So the moment arm of this system, if I remember that this thing is constrained to rotate about the center of this wire, right? The center of this wire too. It rotates like this. That means, let me get a different color for that. That means the center of rotation is right here in the middle of that wire. Right here in the middle of the wire. Of course, it's where I chose to draw the arrow for the current. Right here in the middle of that wire. Fortunately, I've already taken care of the geometry. I've got W over 2 and W over 2. In each of these cases, that distance will be W over 2. But notice in each case, the torque is different because here, the displacement vector from the point of application of the force to the point of rotation, it looks like that. They are completely perpendicular. Here, they are not completely perpendicular. There is a component of this force that is perpendicular and a component that is parallel. And remember, parallel forces cause no torque. You can't open a door by pushing towards the hinges. You've got to push at a right angle to the door, not towards the hinges. And so part of this force is not producing a torque. Part of it is, part of it's not. Here, though, The entirety of the force is directed along the line of action that passes through the center of rotation. So this is like pushing a door, pushing on the edge of a door towards the hinges. This produces no torque. And so here I've got a maximum torque. These are perpendicular, which means the torque is maximized. Here it's less. Here it's minimized. It's 0. And here I have more torque than I had here, but notice the sign has changed. So this seeks to restore, it seeks to reverse the direction of rotation. So if I start here, I will rotate here, and I will rotate on through because of the inertia, but I start to slow down. What is the upshot of this? If this is my apparatus in the magnetic field, and I start out here, I'm going to rotate to here, rotate back. I will do this. I will just oscillate within the magnetic field. That's if my current stays steady and my B field stays steady. Okay, let's talk about how to calculate the torque. So the torque, if you remember from probably quite a bit ago when you studied these things, the torque is equal to, this is how I normally write it, perpendicular force times the displacement from the point of application of the force to the point of summation. In this case, we're going to sum it about the center of rotation, which is right in the middle of that bar. All right, I can take care of the perpendicular aspect here by adding a sine theta over here, where theta is the angle between the force and the displacement. So I'm going to do that. I'm also going to recognize that in this case, the displacement between the point of application of the force, if you can see that, point of application of the force and the center of the rotation is always W over 2. And I'm going to remember that the force is always IAB. So in this case, I get that the torque produced by this force is IAB, that's the force, delta x, which is W over 2 sine theta. Okay, that's the torque produced by this one. Now, because I've put in the sine theta, that covers all of these situations. Theta here is 90 degrees, theta here is less than 90 degrees, theta here is 0 degrees, right? So sine theta, that's going to cover all of these situations. But notice I've only calculated the torque due to one of them. I have another one. The force is oppositely directed, but the torque has the same sign because both of these forces are producing a rotation in the same sense. They both produce a counterclockwise rotation. So I'm going to get the total torque. I need the torque from this one, which I have, plus the torque from this one, which I haven't written down yet. But because of the current is the same, the B field is the same, and the moment momentum is the same, all I need to do is write this down again. This is going to be the same force plus IAB sine of theta. Fair enough. If we see that, let me go to a different page where I have some room and work a little bit of mathematical sorcery. So what I've said is that my torque, make sure I'm on the page, my torque is equal to IAB sine W over 2 sine theta. And then I added another one, so are we okay if I just do this? I added the exact same term. Of course, I'm going to get the over 2 canceling. 2 times 1 over 2 is just 1. But notice I also have some geometry here. A is the side of one of the sides of that rectangle. W is the other side of the rectangle. If I multiply one side of a rectangle by the other side, what do I get? I get the area of that rectangle. So I can write the torque rather simply now. I times A, B, and then sine theta. Where this is the area of the loop. Again, I got this from looking at a specific geometry, but in this case, this turns out to be a general result. So if I have a circle in there, if I have a triangle in there, if I have some strange shape, as long as I know the area of the loop, this equation is still valid. Sine theta now is the angle, remember, between the current and the magnetic field. So this is how you calculate the torque on one loop of current in a magnetic field, IAB sine theta. Now, what if I need a lot of torque? What if I'm doing an application where I need quite a bit of torque? I have, to change the amount of torque I have, I can change one of these things, right? I can make the current bigger. As it turns out, practically speaking, that's pretty expensive. I've got to run a lot of electricity. I probably have to install new equipment. I could also make the magnetic field bigger, but that's even more expensive. I've got to either buy bigger magnets, or if I'm using electromagnets, I've got to increase their current. And so this turns out to be pretty expensive as well. I could increase the area of that loop. Well, that turns out not to be very practical. What if my application needs to fit in a certain box, and I have to increase the area of my loop to 3 times the size of the box? And that doesn't work either. So I'm kind of stuck. Unless I remember that this is the torque on one loop of current, and there's nothing really to prevent me from putting in 2 loops of current, or 3 loops of current, or 4 loops of current. What I'm suggesting is I take my loop, and instead of making it one loop, I construct something that looks something like this. Looks like a spring. Now, the way I'm drawing it, these are pretty far apart, and I didn't draw it very well. In actuality, if I'm going to do this, I would want these to be as close as possible. Why? Because if I'm modeling these as circles, I need them to look pretty close to circles. As it is, the coils of a spring are not circles. They don't connect to each other. But if I'm going to make the approximation, I need to get these really close together. So I'm probably going to use really thin wire, and I'm probably going to sandwich it pretty tightly. Of course, I've got to insulate the wire such that no current runs the wrong direction. But if I do that, this works pretty well for producing more torque. So let's say I have a coil, right? This is what it is a coil. It's also called a solenoid. Let's say I have a solenoid or a coil of N turns of wire. I make N loops. Well, if this is the torque due to one of those, then surely the torque on a solenoid or a loop is just N times this expression. And so I come up with this NIAB sine of theta, where this is what I'm going to use for the torque on a coil of wire, which is consisting of N turns, carrying current I, of cross-sectional area A, and of magnetic field in a magnetic field B. Now, what I haven't talked about yet is what do I do with the oscillation? Because you might have recognized that probably what I want to do is make this thing turn. I'm probably going to want to produce motion, which means I need it to turn. How do I deal with the oscillation? Well, the answer is simple. If the torque is coming from one of these, and what I've said is that for half the cycle, right, when it passes through this point, the torque changes direction. What I would really like is for there to be no torque after it moves to this position. It starts here, it goes here, it goes here where the torque is minimized. If I could somehow turn off the torque, then this thing would continue to rotate through this position just due to its own inertia. And then when it gets back to the position where my torque is right, my torque again produces the motion that I want, if I can turn it back on. So I want to turn off the torque for half of the cycle. I want it to go to this position, and then the torque just disappears, and this thing rotates under its own impetus, and then it gets back to where I can turn the torque back on. How could I do that? Well, if I'm using a direct current circuit, DC, the only way I can really get rid of the torque is to either turn off the current or turn off the magnetic field. Either one of those is going to work. If I turn off the current, this is 0. Turn off the magnetic field, this is 0. So that's what I want to do. As it turns out, practically it's usually easier to turn off the current that's flowing through this wire. Probably what I do is I construct a situation, this is going to be a crude drawing, where if this is the axis of my loop, say this is, what I've drawn is this part. So up here, there's the loop. let's say that I connect this to some sort of conductor which has a break in it. So, let's see how I can draw this. Let's say I have, this is connected to some cylinder and then some cylinder. But these cylinders, I'm not sure if this is easy to see or not. These cylinders have a break in them. So this thing is going to turn, and every now and then this brake will be facing us, and then as it keeps turning, there's no brake, and then there's a brake, and then there's no brake, right? So sort of the space between my fingers can serve as a good analogy. There's a brake, but as this turns, now I don't see a brake, and now I see a brake. And let me connect these, usually with some wire brushes, to a battery. So the wire brushes means that there's not a rigid connection, so I can turn this thing which is in contact with the brushes, but as it moves to this position, right, there's a gap where the brush hits, and so the current gets turned off. But as this thing continues to rotate, sooner or later the other side comes back into contact with the wire brush, current turns back on. So this is they're usually a little bit more complicated than this. This is an example of what we would call a commutator. You don't really need to know that word for this class, but it's handy to have. This is a device that allows you to turn off the current in a DC circuit every half cycle. If something is rotating, you basically hook this up such that there's a gap every half cycle. That enables the current to turn off, killing the torque, and then you don't get a reversal of your motion. The motion continues due to inertia. It will pick back up the current and continue to spin and spin and spin and spin. In effect, you've made a DC motor at this point. AC works a little bit differently, but we don't talk about AC in here. Suffice to say, in AC, the current itself actually changes direction every half cycle, so you don't have that issue to worry about. There are other issues to worry about, but in a DC circuit, this is usually how we handle the need to kill the torque every half cycle. We just turn off the current every half cycle.